Hello, we are Team 13, and we are doing a project for modeling of robots in mechanism analysis and synthesis. My name is Coria.
I'm Mohammed Alali.
And I'm Jason Soto.
Mechanisms and machines have been used since the ancient history to reduce the effort of humanity. And since the Industrial Revolution, it impacted us in all aspects of life. But what's a mechanism? A mechanism is a rigid body connected by joints in order to make a desired force or a motion transmission. And one of the most first famous mechanism was the Watt's linkage, made by James Watt for his piston in the steam engine that he was building. Another example was the 4-bar mechanism. The 4-bar mechanism consisted, as you can see in the figure, of 3 movable rigid bars or links and a fixed frame. The fixed frame adds up as a 4th link or a bar, and that's why it's called a 4-bar mechanism. But before, a long time ago, they used to do it by a graphical methods, a pencil, a ruler, and a compass. But with the father of modern kinetics of mechanism, Ferdinand Frudenstein, he made a revolutionary contribution to the world by applying computers and digital methods to the kinematic synthesis of a mechanism. And by his approach, he made the famous equation of the Frudenstein scalar equation, which led to many inventions and mechanisms we see in these days as the modern mechanisms. As you can see here, the engine, the wheel of the train, and many others.
Analysis of a 4-bar. In the analysis of a 4-bar, typically 8 parameters must be considered. Those parameters include the lengths of the links, as well as the angles, which define them in reference to an x and y coordinate plane. When adding these parameters through the method of vector addition, we result in something known as the loop equation, which is particularly useful and an integral part of further analysis of the system. In addition, when these loop equations are solved, typically 2 solutions are found for every input angle theta. For our particular system, these are the link lengths that we will be using. Link lengths 2 and 3 were chosen beforehand by the professor, while link lengths 1 and 4 were chosen by us, the students. The reasons why we chose these distances is so that the system would satisfy Grashoff's condition of being a type 1 mechanism, which is easier to analyze and predict its behavior. Our system, more specifically, will behave as a double crank, which is shown in the image here. A double crank has 2 cranks, both P and L in this image, and will rotate a full 360 degrees. For our first solution in our system, it will behave as such. The input angle is for the link R2, and it will rotate at a constant rate for 360 degrees, and the link lengths will follow. The second solution, shown on the next slide, is in this animation here. And as you can see, it follows a similar circular path, and link 2 again rotates 360 degrees. The biggest difference between closure 1 and closure 2, or solution 1 and 2, is that they're inversions of each other, but their behavior and their circular path is pretty much the same. For further analysis of the system, an additional link was added to link 2 at a specific angle and distance away from our link 2. This animation here shows the trajectory of the point after, again, the same analysis of a sweep of 360 degrees was inputted the link length 2. Using the output from a SolidWorks simulation and some MATLAB code, we were able to plot the graph of the position of point P, which is the extension of link 2 in Excel, and it looks something like this. As shown in the previous trace path, it's mostly circular, although some parts are slightly flattened out. Even further analysis of the system, we calculated the omegas and the alphas for lengths 3 and 4, that is the angular velocity and the angular acceleration. And as we can see in the tables here, neither the acceleration nor the velocity are linear, meaning that they fluctuate with time, as opposed to the arc link length 2, which has a specific and constant angular velocity. So having an angular velocity in one point does not necessarily guarantee that the angular velocities of the other points will be constant. And as for applications, 4-bar mechanisms have several applications. For our particular system, we chose to animate and show one of its applications through the use of train wheels, shown in this animation here. But there are several different applications which it could have. For example, quick return mechanisms are common uses for double crank mechanisms where an additional link could be added to one of the shafts, as well as engines, and just generally any mechanical system could take advantage of a double crank.
For the slider crank synthesis, we were given points A1B1, A2B2, and A3B3 corresponding to a triangular link. These three positions are defined by the red, green, and blue lines in the diagram. Using positions A1, A2, and A3, we were able to determine the initial position, the position of the primary revolute joint of our slider crank, A0, depicted by the purple circle in the diagram. The synthesis of the slider crank was conducted in MATLAB. What's depicted in the pictures here is a graphical representation of the numerical method used to find the resulting geometry. First, poles P12, P23, and P13 are located, shown by the blue, green, and red asterisk in the first picture. A line was drawn between pole 13 and pole 12, shown by the cyan line in the second picture. Pole 23 was then mirrored across this line to produce the cyan asterisk, or cyan point. Using pole 13, pole 12, and pole 23 prime, which was the mirrored point, we create the circle of slides, and any point C of our secondary link of the slider crank will move in a straight line if it starts on this circle. Once the circle of slides was created, we needed to find an upper range for our mechanism. Many of the points on the circle of slide result in invalid geometry, which is why through iterative testing we found that a valid range for the mechanism is between 0 and 15 centimeters on the lower half of the circle of slides. A partial verification of the mechanisms developed can be obtained through MATLAB by examining the resulting plots and the resulting positions of the links. As you can see here, when x is equal to 9, the red, green, and blue triangles seem to flow together. However, we do not have information about how the blue triangle goes back to position red. This is where SolidWorks came in, and a full verification was conducted with this software. Based on the geometries and the allowable geometries of our system, we decided and concluded that the best application of this specific mechanism was as the crank and connecting rod of a Stirling engine. This Stirling engine, however, has several problems to it. Because of the constraints in our mechanism, the connecting rod is too short when compared to the crankshaft. This results in unnecessarily large strokes when powering the mechanism, which is hard to achieve with the low amount of heat that normal Stirling engines run on. The sliding line is also not perfectly aligned with the primary revolute joint, not allowing the mechanism to obtain energy from the first stroke and the absorption stroke when the gas cools. In conclusion, using a 4-bar analysis, we obtained, based on the 4 link lengths, we obtained a position analysis, a velocity analysis, and an acceleration analysis. And based on these analyses, we determined that the best application for that particular mechanism was a quick return mechanism inside of a train's wheel systems. For a slider crank, after evaluating the possible geometries and finding the sliding line and the possible link lengths, we determined that the mechanism was most suited as the crank and connecting rod of a Stirling engine. Thank you.